Okay, a quick video Thursday morning about fraction addition, but I'm starting looking at this slide. Yesterday we talked about multiplying fractions and made a little video about that. And we noticed when we did that, that the denominator, the 6, is showing up during the process. If I have what is 1/2 of a third, then I started with my third, and I wanted to take a half of this third here. And so I drew a line down the middle and said, let's look at, say, the top half. And where they overlapped, how big was that? And when I'm thinking about it, I have to notice that there are 6 pieces before I can formulate my answer. I have 1 piece out of how many? 1 piece out of 6. My answer is that. The top numbers count how many pieces I'm thinking about. 1 times 1 is 1. And the bottom numbers, the denominators, are how many pieces I'm cutting things into. We started with thirds, and then we did halves the other direction, and where the overlap was 6ths. So before I write my answer, before I can finish thinking about my answer, the denominators are overlapping. They're interfering with each other. They're multiplying. Fraction addition is different. So when I now want to talk about fraction addition, then now the denominators are just thinking about what I have. Let me erase this part. I have 5/8. 1, 2, 3, 4, 5, and I want to add 3 more. So I'm going to pick up those and put them over here. And now I have a whole pie. I have 8/8. So I have 5 somethings plus 3 more somethings is 8 somethings. And I happen to be counting eighths of a pie, but this over 8 is just a label like oranges or apples or bananas or elephants. I have 5 somethings and 3 more somethings, and I get 8 of the somethings. So the denominators are not interacting with each other. There's no overlap. There's no math happening with the denominators like we were doing before, where the actual shape of what we're dealing with was changing in the middle of the process. If I have 5/8 and I want to take away 3/8, it's the same sort of thing. I have 5 things. I'm going to take away 3 of them. And I had the 2 that I shaded green left over. So there's 2 things left. I have 5 things. I take away 3 things. I have 2 things. It doesn't really matter that the race. They could have been bicycles. They could have been sports cars. I'm just counting things. If I have more numbers, then I just want to make a story in my head. I have $11. Someone gives me $9 more. Now I'm up to 20. But I'm spending $5, so I'm down to 15. I'm just counting along the top with increases or decreases. And the fact that I'm dealing with 16ths of a pie doesn't really come into my story. I could have been counting anything else. The issue is that all the denominators have to match. If you ask me what is 3 apples plus 7 oranges, then that's not a sensible question. I can only count things that are the same. And so the difference with fractions and apples and oranges is that the fractions I can actually make to have the same thing, whereas except for maybe a smoothie, I'm not really sure how to combine the apples and oranges. So
unless the question was how many fruits do you have or something, if we then were to switch, but
right,
philosophical.
Do something kind of linguistic. So if I have 14/15 and I take away a 10th, then this isn't quite a math problem in my mind. It's not quite the same kind of thing. I'm not adding and subtracting. It's that I'm stuck. I don't have the same item to be counting. So I'm doing something that, yes, it's math, but it's also sort of not math. It's a preliminary step. I want the bottoms to match. And the simplest way to do this is just to brute force it. If I take one number and multiply it by the other one, so I'll take the 15 and multiply it by the 10, or take the 10 and multiply it by the 15, I am sure they're going to match. Because it doesn't matter the order when I multiply. 10 times 15 and 15 times 10 and 10 times 15 will be the same thing. I happen to know they're 150, but even if I don't know that, I know they will be the same thing because it's just two things multiplied in either order. To be fair, if I multiply the bottom of a fraction by times 10, I also have to multiply the top by times 10. Or if I multiply the bottom of a fraction by times 15, I also have to multiply the top by times 15. So I will get 140 1/50ths minus 15 1/50ths. And then I'm back up to this story. I have $140. I spend $15. I have $125. Then there's this annoying rule that fraction answers should be fully reduced. So in this case, I'm thinking about money. How many quarters for $1.25? That's 5 quarters. How many quarters for $1.50? That's 6 quarters, and I can reduce efficiently. Yeah, I could do divided by 5 and then another divided by 5 as an extra step. If that's how you did this, great. There's no moral virtue to being able to reduce all in one step, but if you can, it's faster. If I have mixed numbers, then it's the same thing, but we have 2 preliminary steps. I can't really do math with mixed numbers. They're annoying. I have to change them into improper fractions. So my first step is to say, I want to take both of these mixed numbers and turn them into the same value written as an improper fraction. So 7 times 3 is 21, plus 2 is 23/3. 8 times 2 is 16, plus 1 is 17/2. And now we're back to this situation where I want to do some fraction addition or subtraction, but I can't get started yet. It doesn't make sense to count more or less of something unless they're the same kind of things. So I'll do the same trick. I'll take each denominator, multiply it by the other one. Whatever I do on the bottom, I have to do on the top to be fair. And then once I have the same thing on the bottom, I can add up 46 and 51 is 97. And we're done. So that's basic fraction addition. And
the one exception to what you were saying there about how not wanting to add or subtract mixed numbers is if the denominator of the fractions are different. The textbook is suggesting that if they're the same, then just go ahead and add the whole numbers first and then add the fractions. So this is about when the fractions have different denominators, so you need to find the common denominators, right?
Yes. And it's also true. Let me write more. So this is getting a little philosophical. If you don't like it, then just skip over it. Over in this box, I'm going to do something. I could do this problem a different way. I could say we're going to add up the 7 plus the 8, and we're also going to add up the 2/3 plus the 1/2.
Right.
And so the 7 and 8 will be 15. And then what's happening with the 2/3 and the 1/2? Well, I'll want to do just what I did before. Let's change them to have a common denominator. And I will get 15 and 7/6. And that looks a little awkward. I'm going to take 6 out of the 6ths and make a whole. So we're up to 16 wholes, and there's 1/6 left over. And I'd probably write that as 16 and 1/6 as a mixed number. So in my real life, if I am doing baking and carpentry, I like mixed numbers. If I'm doing physics or computer programming, I like improper fractions. And I don't know what your career affiliation is. So if you want to write this as a improper fraction, great. If you want to write it as a mixed number, great. They are equally valid answers. You can go from one to the other. I happen to think what I wrote in red is a little bit simpler than doing what I wrote in black. And then as a final step, making it a mixed number. But either way works.
It seemed like the textbook was suggesting that since the original problem was given as a mixed number, that our final answer should also be a mixed number, at least as a general thing of what they're looking for.
Could be, but I don't really care what they want.
Okay.
Yeah, there are plenty of computer applications where you want the user to input something as mixed numbers because that's how people are thinking about it, but the behind the scenes math has to be done with improper
Yeah,
fractions.
for
And
sure.
there's even some baking applications where I'm scaling a recipe up and I get
Mhm.
some absurd number of sixths and I want to know, well, how many cups is that really?
Yeah.
So, in real life, you can start with one and move to the other. It's not always true. You stick with what they gave you.
Yep. Thanks.
Okay, but what do I do to be efficient about this? There's an example in the book that talks about the LCD, and all they give you is this little bit here, which doesn't explain things clearly. So I'm going to explain that better. Because we have only had one method so far. Let's multiply each denominator by the other. And that can work, but we get pretty big numbers like 150, which we sometimes don't want. So there's, in our website, if we go to Mad Science, Smushing Numbers Together, the girl with the chemistry stuff, and fraction addition and subtraction, I'm skipping a bunch because I'm assuming you know these things. There's 3 methods for adding fractions. So let's look at that. The brute force method is what we just talked about. We're just going to multiply each denominator by the other. And that's fine. Oops, it works great. It starts out very fast, but it also slows down. So I will say, we'll do 1/30. When I'm writing it, I'm not going to put my plus right here. I need some space to do the times something top and bottom. So I'll make myself have a little bit of space before the plus. 1/42. I don't want to think about things at all. I'm going to brute force this, dive right into it. This one I do times 42. This one I do times 30. Multiply each by the other. I have to be fair, so whatever I do on the bottom, I have to do on the top. And now I get 42 over something and 30 over something, and I'm starting to slow down. I'm paying the price for not having to do any thinking earlier. So first I need to figure out what is 42 times 30. Well, 4 30s is 120. 2 more 30s is going to be 60. So I'm up to 180. No, I'm thinking wrong. 40 30s is 1,200. Let me just write it out and not try and show off in my hand. Okay, so 2, 6, 3, 4, there we go, 1260. Okay, and then I have 72 over 1260. And I want to be done, but I need to reduce this. So what am I going to do? I can use my divisibility rules, and notice when I add up digits that 9 is going to go into both of them, or 3 or 6. So maybe I'll start with 9. 9 times 8 is 72. With a 1260. Oh, 36, so that's going to be 40. And then I can reduce again by 4, and I reduce by 8. I'm not sure yet. So 25 4s is 100, and 10 more, so 35, and we're done. Okay, so brute force method, we started without having to think at all, multiply each denominator by the other, and then keep it fair. But quickly we got bogged down by these big numbers. And at the end, when we had to reduce, we had to do a bunch of reducing. The next way we can do things is a list of multiples. if I want to find a common denominator for 30 and 42, this one, well, let's just look at all the multiples. So for 30, I have 30, 60, 90, 120, 50. I'm just adding 30 every time. And I'm running out of room, so hopefully that's good enough. For 42, a little bit trickier to do the math in my head. 42 and 42 would be 84. Another 40 would be 120, so 126. Another 42 would be 168. Another 42, well, 40 would get me up to 200, so 210. Aha! Look at this. 210 is in both lists. It's the first multiple that was common to both. It's the least common multiple. So I know that my answer is going to have something over 210 and something over 210. That's nice. That's a lot more of a friendly number than 1,260. So what do I need to do? This is times 1, 2, 3, 4, 5, 6. That's a times 7. And this one times 1, 2, 3, 4, 5 is a times 5. So we'll wind up with a 7 here and a 5 here. Remember my divisibility rules. This one is even. Its digits add up to a multiple of 3. So 2 works, 3 works, so 6 will also work. And I'm at my 2/35 already. I could divide by 2 and then divide by 3 and make more steps too. So in this method, I had to do some work, but some people really like multiplying. Making this list of factors doesn't seem like as mentally painful a chore as what we did on the other page. So make a list of multiples, pick the first one on both lists, and that's what we're going to use. The last way to do things is prime factorizations. So again, I have 1/30 and 1/42. And I'm going to make factor trees for each thing. So 30 is going to be 6 times 5. 6 I will break down as 2 times 3. 42, on the other hand, is 6 times 7. Now I want to take the factors that repeat on both trees and not double count them. So we have a 2, and that's great. We don't need that 2 also. We have a 3, and that's great. We don't need that 3 also. We have a 5. Okay, I don't see any 5s over here to cancel out. We also have a 7. So I go back to the first tree. Do I have a 7 to cancel out? No. So once I put everything together, the 2 times the 3 times the 5 that I highlight, and then the times the 7, that's going to give me the 210 that we got before. Some people like division, and this with doing division to make factor trees, they think is a faster, better, friendlier way to get to that 210 than making a list of multiples. It's all up to what style you like better. So again, I'm going to have something over 210 and something over 210. If you do this a bunch, you will notice, wait a minute, I don't actually care that we broke up the 6 into 2 and 3. So I could be even more efficient and say what I really want is to make sort of part of a factor tree. And all I want to know is what things are in common and what things are different. So this is the common 6 with a 5, and this is the common 6 with a 7. And then I will do the same thing. Well, one of these I will keep, and because it's on the other tree, I will get rid of it. And the fact that it's a 6 bundled up and not the 2 times 3 separately, it still works just the same as what I showed you. So I will do my 6, but not both of them, times 5 times 7, and get my 210 that way. And the advantage of that shortcut is not only that I don't have to write as much, but now it's very easy to see that, oh, this factor tree is missing the 7. And this factor tree with the 42 is missing the 5. Other than that, they were the same. Oops, and I forgot a plus. And now we're back to where we were before. I mentioned it's okay to reduce in 2 different steps, so I will do that for people who like that this time. And of course, it's the same answer, and there we go. So if you have done a bunch of these, this tends to be the fastest method, this third one about prime factorization, because you will quickly train your brain to say, this is what's in common, and then here's the part that's not in common for the 2 factor trees. If you have to go all the way down the factor tree to finish it, that also works, as we saw earlier. It just means it's a little less obvious what numbers to put here. So 3 different ways to do common denominators. They all work. They all have their pros and cons. Some start quickly and bog down. Some start with a lot of thought, but then are pretty efficient at the end. And what the book was going to try and explain was just this third one about finding the factor trees and saying, I don't need 2 2s. Let's just do 1 2 times. Let me actually draw. I am saying it poorly. So we have 6, which is what's in common, the 2 and a 3. We have 4, which is what's in common, the 2 and another 2. Since we have this 2, we don't need that one. And then there's a 3 and a 2 without a match. So we multiply the 3 ones together, 2 and 3, and the 2 we're keeping, and we get to 12. So that's what they're trying to explain, but writing it in a kind of confusing way.
Especially writing it with the squared sort of doesn't show you the shorthand of that we have the 2 2s together. I mean, it does, but it makes it a little bit confusing.
Yes.
Thanks, that was much more clear.
So do any of these 3 work? You don't have to learn all 3, pick your favorite. And it's important that you can follow all 3, because whoever your math teacher is, or whoever you're working with at a study group might like a method that you don't use. So be sure you could follow somebody else writing any of these 3 methods. But for you doing your own work, just pick your favorite.
Thanks, that was really